Okay, final part of chapter 15. The other two parts of your inner ear are used to determine your balance, either your kinetic balance, your moving balance, where's your head relative to space, or static balance, which is going to be if you're standing still, which way is gravity yanking on you. So the static labyrinth, the first of the two, is located in the vestibule, which is here. Okay, that big bulby thing at the end of our snail shell. The kinetic labyrinth, the moving labyrinth, is actually located in the semicircular canals ampulla. If you look at the semicircular canals, you'll notice that, like in geometry, they're on the three-dimensional plane. You've got one on the x-axis, one on the y-axis, and one on the z-axis, which if we're talking about the movement of something in 3 dimensions, it makes sense. So the static labyrinth, like I said, it's located in the vestibule. Internally, there are 2 functional units, the urticle and the saccule, okay? They have 2 primary functions. One, what's the position of your head relative to gravity? Are you standing straight up and gravity's pulling down? Are you laying face forward and you're being pulled forward? The other is responding to linear acceleration and deceleration. So if you've ever been asleep in a car and the car stops and you wake up and, nobody woke you up, that's a good example of that. Your body knows that you've stopped moving because of the static labyrinth, okay? As I said, the kinetic labyrinth is located in the semicircular canals, and it evaluates the movement of your head. Which way is your head tilting? Which way is your head moving? So let's start with the static labyrinth, okay? The urticle and the saccule are actually simple cuboidal epithelium. They contain a specialized patch of epithelium called the macula. And you've got the macula urticle and the macula saccule, okay? So if this is your head, all right, the macula urticle is basically oriented parallel to the base of your skull. So this top one is basically the same. The saccule, however, is actually oriented perpendicular to the base of your skull. Okay, so you've got 2 separate bits of information coming in. So the static labyrinth with the macula, you have hair cells like you saw previously in the organ of Corti, okay? But they're embedded in this gelatinous matrix that contains these things in here called otoliths, okay? It does resemble the spiral organ in the fact that you've got a column of supporting cells, the pink cells that you see, supporting the hair cells. The numerous hair cells actually have the same type of stereocilia, those little hairs sticking out, and one kinocilium, which is this bumpy looking one that you can see up here. These hairs are embedded in that gelatinous matrix, and that gelatinous matrix is weighted by those otoliths. In other words, it's got enough girth to it that if gravity yanks, it's going to move, okay? So the gelatinous mass moves in response to gravity because of those embedded otoliths. Those embedded otoliths are going to basically cause those hairs to bend, okay? So if this shifts this way, the hairs bend this way because I am literally embedded in that gel. If it shifts that way, the hairs are going to go that way because they are embedded inside of that gel that has the otoliths that give it weight. So if the hairs bend toward the kinocilium, this direction, there's depolarization. You get an action potential. If, on the other hand, they go the other way, they go toward the short hairs instead of toward the long hairs, you get hyperpolarization. Again, that's more negative inside the cell than what you started with. The hair cells are synapsed. You can see the little nerve endings here, the neurons coming in here, the nerve fibers. They're synapsed with the vestibulocochlear nerve, and they use glutamate as a neurotransmitter. So the pattern of stimulation gives you specific information about your head's position and whether you are accelerating or decelerating, whether you're moving forward or you're stopping. And in response, the muscles in your body will change the tone of your back and your neck. Everybody here has fallen asleep in class, don't lie. And you start to your body starts to go back and you go, huh, right? And you sit yourself up real quick. That's actually this right here. Those otoliths shift and it sends a signal to your brain of you're going backwards, and whoa, you pick yourself up really, really quickly. So we've got the macula urticle. Remember, I said that with the macula urticle, it's the same. It's parallel with the base of your skull, right? So if you're holding your head straight like this guy is here, notice that this isn't shifting in any particular direction. The hairs aren't getting pulled. So this particular organ is not sending signal. But when you put your head down like this, all of a sudden, this base of your skull is now facing that direction, right? So the otoliths and that gelatinous mass shift bend those hairs, and their signals sent up to your brain of your head just shifted. Now, the macula saccule. Remember that with the macula saccule, here's the base of your skull. This is this way. It's perpendicular to that. It's not in the same direction. So if your skull is facing up, this is already going to be bent because it's sitting up like this. However, when you bend your head down, now this part of your skull is more flat, right? Because you're looking down. So that gelatinous mass stops being pulled on by gravity and no signal is going. If you combine the two, you get twice the amount of information about where your head is positioned relative to gravity. Okay, let's talk kinetic labyrinth. We've got these semicircular canals, right? On the X, the Y, and the Z axis. At the base, you've got this thing called an ampulla. Okay. As I said, they're on the X, the Y, and the Z plane. And that means that no matter what movement you do in the 3 dimensions, you've got information on it. So in the ampulla, okay, you have a specialized form of sensory organ called a crista ampullaris. Looks like this. Okay. You have hair cells. They're a bit different than what we've seen before, but you also have that nerve fiber at the base. So the hair cell is different. It's not like your classic neuron, but I've got a receiver to receive my signal. So when, well, hang on a second. The crista ampullaris, which is not helpful, go back. The crista ampullaris makes that kind of ridge crest right here, okay? And you've got this gelatinous mass on top called the cupola. Kind of looks like a teardrop up here, all right? Notice that within that gelatinous mass, there are no otoliths. There is no weight added to it, okay? So the crista's hair cells, these guys, are embedded in that gelatinous mass. Okay. The cupola only gets displaced when the fluid inside the ears shifts in response to movement of your head. So if I'm doing a front handspring, okay, when that fluid gets pushed back because I'm going forward like this, that cupola bends because the fluid rushing by it makes it bend. So the cupola movement, it bends the hair cells, and that's what initiates the action potential. The response to movement is largely unconscious. If we're moving, we tend to kind of correct that movement before we actually realize we're doing it. So, the sensory axons from the vestibular ganglion pass through the vestibular nerve to the vestibular nucleus, which also receives input from several other sources, such as proprioception from the legs. Remember that proprioception is just body position. It's a real fancy way of saying body position. So, you're getting information not only from your ears, but from your body parts. The vestibular neurons send axons to the cerebellum. Remember, the cerebellum is the broccoli stem back here, okay, which influences your posture. It basically helps to correct it. The vestibular neurons also send axons to the motor nuclei. The motor nuclei, number 3, including your eye movement, the trochlear and the abducent nerves, which control muscles in your eye and stuff like that. That's going to move your eyes as you move, basically. The vestibular neurons also send axons to the posterior ventral nucleus of the thalamus, which is up here. And the thalamic neurons actually project to the vestibular area of the cortex, which is up here. Your body has a lot of incoming information. Your brain is the one that has to kind of put it all together. One of the reasons people get motion sick is because your eyes are seeing one thing, your ears are moving and feeling something different, and your brain goes, I don't know what to vomit. I don't know what to tell you, because literally you're getting two really conflicting signals. So, the effects of aging on the special senses. There's usually a decline in everything. Your vision starts to go, your hearing starts to go, even taste. You don't taste as well as you used to. If you've ever been around a geriatric person and they're making a meal, normally that meal will be overspiced, oversalted, and it's because they don't taste as well as they used to. With all of those declines, a lot of times in older people and geriatric patients, you will find they lose their appetite. They don't taste things like they used to. It doesn't taste as good as it used to. So imagine eating tasteless mush every single day. They don't want to eat because it's not pleasurable anymore. Visual impairment, we get glasses as we get older. It's just a fact of life. Disorientation. You've got an inability to balance, actually. That inability to balance is caused by the aging process of the vestibule and the semicircular canals. And as you age, your ability to balance doesn't work as well. Now, finally, with that disorientation, you increase your risk of falling. Geriatric patients have a risk of falling, not because they're clumsy, but because they're losing their ability to use the semicircular canals in the vestibule to establish their balance.